Okay, let's get started. Sorry about that delay. And this is a cozy room. Is everyone comfortable? No? So you need a chair. There's a chair right by Rachada. Is there another one? Anybody has an empty chair next to him or her? Oh, well. So there's one right by Rachada. One of you can go. And there's one over here. There you go. I don't need to sit. There you go. Yeah. And for now, we're okay, but I'm not sure if we can accommodate the next person. There you go. All right, yeah. We'll find a way, hopefully, for the next class. Okay, this is computer architecture, and I hope you're here for this, basically. Well, I hope you've taken 213 or 243. Who's taken 243 here? Nobody's that old. That's good. So I'll have to update my slide such that this is gone now. It used to be 243, the systems course. Now it's only 213. And in 213, you've seen C as a model of computation, right? And I hope, well, you've seen the programmer's view of how a computer system works in that class. And you've also taken, hopefully, it's a prerequisite, 240, in which we had digital logic as a model of computation, as a model of getting things done. And you saw a hardware designer's view of how a computer system actually works, how a computer system is designed. In fact, you designed a computer system. Maybe not the full thing, but components of it, right? Well, in this class, you'll actually bridge the gap. We'll talk about what happens in between. What is the interface between the programmer and the hardware? And how does an assembly program end up executing as digital logic? Actually, how does a C program end up executing as digital logic if you bridge the gap between C and assembly as well? And how is a computer designed using logic gates and wire to satisfy specific goals? Well, the first goal is to actually functionally execute the program correctly, right? But also other goals as execute it fast, execute it energy efficiently, execute it reliably. For example, you would like to design a computer that doesn't give you a Sprite if you ask for iced tea. That's what the computer outside did to me. So I'm stuck with Sprite now. I guess we'll make do today. And you'll basically see micro-architect's view instead of programmers and hardware designers. But you'll be very conscious of the programmers as well as hardware designers' view in this class. What is the micro-architect's view? Basically, the key question is how do you design a computer system that meets some of the system design goals that we will see. We'll call it a design point. The set of design goals that you need to meet to actually design a specific computer system. And the choices that the architect or micro-architect makes over here in between critically affects the life of the programmer as well as the hardware designer. You can make life terrible for the programmer and easy for the hardware designer. You can make life easy for the hardware designer and terrible. Well, you can make life terrible for the hardware designer and easy for the programmer. These are two extremes. And computer architecture is a trade-off within that space, actually. Whose life do you make really hard? And actually, computer architects can span the two also. Sometimes architect becomes a programmer as well, and architect becomes a hardware designer too. So keep this in mind. This is the first slide of this course, and this gets to the crux of computer architecture. It's really a system of trade-offs, and whatever choice you make in between critically affects what happens up and what happens down. So let's take a look at some of those choices. So what actually is up and what actually is down? This is kind of a wishy-washy example over here, but we have a much more structured way of designing computer systems today. Well, and those are called the levels of transformation. How many of you are aware of this? Okay, good, I guess. That's why you're here. So, are you ever Richard Hamming? Do you know the name, Hamming? Hamming codes, Hamming distance. Yeah, he's a very, very famous guy. He has a cat too, a black cat, basically. This is Richard Hamming. He actually made a lot of contributions to computer science. Hamming codes is one of them. Error correcting codes. Hamming distance is another of them. Do you know Hamming distance? It's a very simple concept. How many of you do? How many of you don't? Okay, good. Feel free to say that you don't know something. That's very important for learning, right? If you don't know, you don't know. I'll say that too when I don't know something. So Hamming distance, it's a very easy concept, so I'll briefly talk about it. It's not a computer architecture concept, but it's basically if you have two strings of equal length, it tells you at how many locations those two strings differ. That's it, basically. It could be any strings. It could be a binary string, for example. For example, the binary representation of 16 with 4, I don't know, how many bits should we use? We should use 4 bits. Well, we cannot represent 16 with 4 bits, right? So you need at least 5 bits. 1, 2, 4, 8, 16, right? Well, let's make it, for the fun of it, 8 bits, right? This is the binary representation of 16. And the binary representation of, I guess, 24 is this, right? 0, 0, 1, 1, 0, 0, 0, 0. Right. Hamming distance, what's the, oh, did I do something wrong? Yes, you're right. So the Hamming distance of these two values in binary, what is that? It's essentially 1, right? Because basically these two strings in binary differ in only one position, which is this one. So Hamming distance of binary representation of 16 and binary representation of 24 is 1. Right? That's the idea. If you look at the Hamming distance, if you treat these as strings in decimal, and if you look at the Hamming distance of these two values in decimal, what is the Hamming distance, assuming a string length of 2? 2, right? Because if you look at this character in the string, they differ. It differs. If you look at this location in the two strings, they also differ. So the Hamming distance of the decimal representation of 16 and the decimal representation of 24, assuming 2 characters per string, is actually 2, right? So that's the idea of Hamming distance. And it's actually used for many other concepts like Hamming codes, which I'll not talk about. But Hamming is the person who introduced this concept. Anyway, I'll digress a lot in this course, but I think some of these concepts are actually extremely important to know, like Hamming distance. You might get a question in the exam, so you'd better pay attention. Although you're paying attention, this is the first day of class. OK, so Hamming also said the purpose of computing is insight. So why do we do all of this? In order to gain some insight in the end, right? How do we gain insight? Well, we'd like to answer some questions, basically solve some problems that we have in life, right? Or make life better. Basically, that's what the levels of transformation is about. We gain and generate insight by solving problems. But somehow we need to ensure that these problems are solved by a substrate, right? And that substrate is really a physical substrate where electrons move somehow, right? So somehow we need to convey our problem at the very top, at human level, in our heads, to the electrons. How do we do that? Well, we cannot talk to each individual electron and say, electron, solve my problem, or collection of electrons, solve my problem. Obviously, that's not going to happen. So people have built this levels of transformation where a problem is translated into an algorithm, right? Such that now we're putting structure into the problem, because an algorithm is something that has specific properties, right? It's a step-by-step procedure that has 3 properties. Does anybody know what those 3 properties are? You've taken basic computer science, right, or computer engineering. 240 and 213 don't cover this? Not yet. OK, that's why you're here. That's good. You'll learn something here. So an algorithm actually has it's a step-by-step procedure that has 3 properties. One is each step needs to be effectively computable, right, by a computer in this case. So by a Turing machine in this case, actually. For example, if you're trying to get from here to, I don't know, New York, fly is not a good step, right? Well, fly like on your own is not a good step, right? But if you have a step that says go to the plane and fly with the plane, fly on the plane, that'll work, right? So that's the difference between effective computability of 2 potential steps. So fly on your own doesn't work. The second is it should be definite. It should be precisely stated, right? Every step should be precise. So, for example, if the step says, run fast, right? That's not definite, right? What is fast? My fast is very different from your fast, probably, right? Whereas the step says, run, I don't know, 5 miles per hour. That's at least a step. It may not be effectively computable for everyone, but it's a definite step. And the third property of the algorithm is really finiteness. It needs to end, right? It needs to have, it cannot have an infinite loop. Okay, so a problem is translated into algorithms, but algorithms are not understood by the electrons either, right? So we take the algorithm and create a program. Somebody creates a program using a language, and there are an array of languages that are available to people. And after that, the program is translated by a compiler to be executed on a runtime system. And I wanted to keep this very general because the program goes through, interacts with many things, right? You compile the program, you get a binary, but then that program interacts with the operating system, virtual machine, the memory manager, etc. It gets executed on the substrate that I call the runtime system, which is an increasingly important substrate today. And then, how does the runtime system actually communicate the program's instructions to the hardware? It goes through the ISA. That's the instruction set architecture, or architecture in general. And we'll cover a lot of this. These are basically the instructions that the machine can understand. How are those instructions implemented? Well, that's defined by the microarchitecture. This is the implementation of the commands or the instructions that are specified by the ISA. ISA is actually the hardware-software interface. It's the interface between the software and the hardware components. Microarchitecture is the implementation of the architecture. For example, we'll cover several ISAs in the first few lectures. x86 is one of the most popular ISAs today. Right? It has many, many implementations. AMD, Advanced Micro Device, has one implementation. Intel has another implementation that's very different. What's going on there? All right. Intel actually has many, many implementations that have been different, right? Pentium, 486. You guys remember 486? Oh, that's good. I don't feel that old now. I guess you must be a hobbyist of 486 because it's very old. So there are many implementations of the same ISA, and we'll cover that. But microarchitecture also cannot communicate directly with the electrons, right? Microarchitecture, the implementation actually gets implemented in the logic gates. These are the gates. And logic eventually gets implemented in circuits, the transistors. And transistors operate based on the principles of the electrons, the device physics underneath. So this is the transformation hierarchy, if you will, or the levels of transformation through which computing, at least general purpose computing today, works. A problem gets translated through different levels such that the electrons can solve the problem. Well, in this course, we're going to cover basically these components. Let's see if we can fix this. Does this mean that we're generating a lot of heat? Now the computer has a problem, right? Actually, I'm not sure if my next slide is, my next slide doesn't have that. So the computing system, actually I'll skip to that given that that computer did that. So in this course we'll cover this part mostly. We'll mainly focus on the architecture and microarchitecture, but we'll dabble into logic, a little bit of circuits, and we'll also go up in the hierarchy. But we'll never forget the top parts of the hierarchy and the bottom parts of the hierarchy. But let me go into a very later slide just to broaden your thinking a little bit. And yes, we're going to cover all of these slides today. It's really not that simple, right? The user actually interacts with the computer too. And the computer, obviously that guy, interacts with the user too. So this transformation levels have interactions with the user. And going forward, it's good to think about how do you design computers and how do you change this transformation hierarchy such that the users can be happier, right? And maybe the computers can be happier too. Okay. I guess while we're at this, one more thing over here is this is the general purpose transformation hierarchy. there have been many proposals. Architecture is a very rich field. There have been many proposals that take the program, implement in some language, and that directly translate it to logic gates. Well, there needs to be some component over here, obviously, that translator, if you will, without going through an instruction set. For example, reconfigurable logic, field programmable gate arrays are programmed that way, right? You can implement an ISA, instruction set architecture, on top of that substrate, but you can directly take the program and implement in hardware. So keep in mind that this is one way of looking at computing. This is the most general purpose and common way as used today. And why is it most general purpose and common? Because this creates abstractions, right? And abstraction is powerful. This levels of transformation create abstractions. Well, what is abstraction? Basically, a higher level only needs to know about the interface to the lower level, not how the lower level is actually implemented, right? For example, when you write programs, you don't really need to know about how they're compiled, right? Well, you can be more effective if you know about it, but you don't have to know about it. When a programmer writes a program, they don't need to know about how the circuits operate underneath. This is very powerful because it saves time, right? Well, I guess I've shown you here. High-level language programmer does not really need to know what the ISA is and how a computer executes instructions. Right? It's great in one way. And the benefit of this is it improves productivity. If everybody needed to know about everything in this computing stack, then everybody would be studying forever, right? Instead of writing programs. So that's the upside. No need to worry about decisions made in underlying levels. Somebody else does that, and hopefully they'll do a good job. And the interface is clean, such that you can specify your goals. One example is programming. Well, this still keeps the abstraction, but programming in Java versus C versus assembly versus binary. Right? How many of you have programmed in binary, like ones and zeros? None? Well, I'll make you do it in this class. We'll program a simple computer called LC3B specifically. And you'll actually program the control signals. And I'll make you do it tediously. So don't complain. But actually, binary is not the lowest level. You can actually specify the control signals of every transistor that's implemented every cycle, right? That's even worse. So if you didn't have that abstraction layer of assembly language, or language compiled into assembly language, which gets compiled into binary, which gets compiled into control signals, then you would have to specify the control signals of every transistor. Right? So your productivity would go down. It would tank. So that's great. We have those abstraction levels. Then why are you taking this course, right? Well, you could be taking this course to actually design what goes underneath. That's one purpose. But even if you're not taking this course to design what goes underneath, it's still important to know what goes on underneath, or even above, right? So it's good to have that perspective that you're designing something in between, but it's good to know how it affects the programmer and how it affects the underlying layer. So I'll give you some examples of that. So why do you want to do that? Basically, as long as everything goes well, not knowing what happens in the underlying level is not a problem. Right? At least from it depends on your perspective. If you're a user who wants to get an iced tea, and if you get a Sprite, something has not gone well, right? If I got my iced tea, I didn't need to know about how that machine operates, for example, right? But I didn't get my iced tea. I got my Sprite. Well, this is not my Sprite. This is the Sprite I was given. So something is wrong, and I really want to know why that thing gave me Sprite instead of iced tea, right? Maybe someone displayed iced tea over there instead of Sprite, right? Maybe it's not a problem with the computer itself. Maybe it's a problem with the computer itself. Maybe something was wrong over there in software or hardware, right? But I don't know. So exactly because of this, exactly because there is a problem, I need to know what's going on in the underlying level. And let's take a look at some examples of this. For example, what if you write a program and it's running really slowly, and you have no idea why? Well, it's gone through all of these transformations. If you know how those transformations transformed your program, then you could do something about it. Perhaps you could write your program such that the underlying levels can optimize it much better. Right? For example, one example of this we'll cover when we get to caching is modern computers have caches. They don't go to memory for every reference. What they do is if they go to memory to get a reference when you load something, they store it in hardware close to the processor in anticipation that that location will be accessed again. This is the temporal locality principle. And a lot of computing is based on this principle. If you access something, you're going to likely access that again very soon. So why don't you design the hardware such that it has a buffer very close to the processor, not far away from the processor, such that that buffer keeps recently accessed words or data values. Now, if you know this, you can write your program such that you can maximally utilize that buffer, right? Because that buffer is of limited size. And you can try to access things that are going to be access a working set, if you will, access a set of data elements and maximally use those data elements as much as possible before moving on to some other set of data elements. Right? So now you know maybe your program is running slow because you're overflowing that buffer. Right? But if you restructure your program, you can be much faster. So knowing what happens underneath enables you to do much better things. There are worse issues, right? The program you wrote does not run correctly, right? This could be an issue too, and we'll see that when we talk about multiprocessors. This may not be. This may be something that you cannot think of right now. Does that happen? Does it ever happen to you? When you didn't have a bug in your program? No? Once? Yeah. It may be due to other reasons. Even if you don't have a bug in your program, usually this happens because you have a bug in your program. But even if you don't have a bug in your program, the hardware may be faulty, right? Maybe there's an error that happens somewhere. Right? It doesn't happen very often. Don't bank on that. The first thing you should look at is when your program doesn't run correctly is, oh, maybe I made a mistake. Let me debug it first. But increasingly, hardware is becoming unreliable too. So maybe there's something going on underneath. Right? And if you're actually programming a multiprocessor program, multi-threaded program, these bugs are more likely to happen because the specification of the underlying architecture is such that it doesn't guarantee all kinds of executions. If this is not clear to you, hold on for a while. We'll cover this in lecture 23 or something when we get to multiprocessor consistency. Okay, what if the program you wrote consumes too much energy? You're writing an iPhone application or some Android application, and it's hogging all your battery, right? Well, and you don't know how to fix it. If you know what's going on underneath, how is this iPhone executing your program, maybe you can do much better. Right? Okay, I'll give you some more specific examples, but this goes on. This is the software side of it. And this is the hardware side of it also. You've designed some chip. You think it's the greatest chip of the world, right? 1,000-core processor with very wimpy cores, simple cores. We'll cover that. And it turns out the programmers are taking your chip and banging their heads on it and are unable to do anything with it. And eventually your chip is thrown into the trash can. Right? Well, you have a problem, right? You haven't considered what goes on above you. You haven't made life easy for the programmer to take advantage of all of those resources that you think are great. Right? And this is the problem that industry is facing today. It has become very difficult to design chips that are easy to program, single-threaded programs that execute the single-thread programs fast. So industry has gone into what's known as multi-core. I'm sure you're aware of it. You have multiple processors on chip. But now if the programmer wants to execute the program fast, they need to divide the program such that it can be executed fast by multiple processors. Basically, you need to multi-thread your program. And this is much harder to do, at least for most human beings today. And there are levels of hardness also. You could make it a little bit easier, or you could say, I don't care. My hardware design is going to be very simple, and it's the job of the programmer to actually program this thing. I don't care how. That's one design choice. But in general purpose computing, it hasn't worked well. It's very unlikely that it's going to work well going forward into the future. Okay, what if the hardware you designed is too slow because it doesn't provide the right primitives to the software? Actually, it could be hard to program because it doesn't provide the right primitives to the software or right interface to the software. It could be too slow because of that also. Maybe, for example, let me give you an example. If the hardware, we'll see examples of hardware providing instructions to better utilize the cache. Right? I just told you about the cache. If you don't have an instruction that says, keep this in the cache, load this, and I'm very likely going to use this. If you do not have that instruction, then the software is less powerful, right? Whereas if you have an instruction that says that, and if you have another instruction that says, load this data and don't keep it in the cache, now the software can be much more powerful, right? Because if the programmer knows what they're doing, they can, if the data is going to be reused by the program, they can use the first instruction, keep this in the cache. If they know that they're loading data that's not going to be used later in the program, they can use the second instruction, load this data, but don't keep it in the cache. Throw it away. I'm not going to use it. Now the programmer or the compiler can optimize the program much better, right? And this is one primitive that the hardware can provide to the programmer or the software. Okay. What if? There's another what if. This is the hardware point of this software point of view. This is the hardware point of view. But what if, as a system designer, you want to design a much more efficient and higher performance system? Again, you really would like to know the entire transformation hierarchy. And I'll give you an example of this later on. Basically, in today's systems, if you really want to optimize a design, you really need to cross the boundaries, cross these transformation layers, and expose information from the lower layers to the upper layers, and expose information from the upper layers to the lower layers. And we'll see many examples of this in this course. This primitive, for example, that says keep this data in the cache or don't keep this data in the cache is one primitive that exposes information from the higher layers to the upper layers and exposes an interface from the lower layer to the upper layer such that the information that's available to the programmer can be conveyed to the bottom. And you can get a much better, much more efficient and higher performance system in general. Of course, so what is the downside? If you would like to do that, if you would like to combine the layers. Exactly. You need to know more. It's more difficult. And there's one more thing. It's more complex. The complexity of the system increases. Right? So you need to find the right interfaces. And the cost potentially can increase also. Because if you didn't have that primitive into the cache, your cache would be simpler, right? Okay. So two key goals of this course are, well, basically, we'd like to cross the abstraction layers. One key goal is to understand how a processor works underneath the software layer that's below the 213, and how decisions made in hardware affect the software and the programmer. Basically, how the decisions you make at the logic layer affect upper layers. And the second key goal is to enable you to be comfortable in making design and optimization decisions that cross boundaries of different layers and system components. And I'll give you examples of this. Let's see how we're doing on time. What time is it? 12:05. Okay, good. 1:05. I guess we could be going backwards in time, right? All right. Okay, I'll try to take a break since it's getting really hot over here. Do you have a place to sit? Ground is good, or you can sit next to me. Up to you. Okay. Let me give you a couple of examples of what we're going to cover in this course. Eventually, I'll talk about logistics, hopefully. But I don't want to keep you over 2 hours here. So this is an example multi-core system. This is actually an old one. It's the AMD Barcelona from 2004 or 6 or so. And if you look at this, it consists of multiple cores, which we're going to cover. Actually, you're going to design a core. It consists of caches. Well, this is the L2 cache. It actually has L1, level 1 cache inside the core. And you'll learn at the end of this course that L1 cache is tightly integrated with the core, and that's why I don't cover it. I don't show it over here. L2 caches, and it has a shared L3 cache. The cache is shared between the cores over here. It has some interconnect, which we're going to talk about also. And it has a memory controller over here, and it has a DRAM interface. Memory is designed with dynamic random access memory technology, and this is the off-chip DRAM over here. This is an example multi-core chip. And the cores actually share some resources. They share the L3 cache in this case, and the requests that miss in the L3 cache go through the memory controller, and different cores can have requests that go to the memory controller, and that can be accessed from DRAM. So we actually did this experiment a long time ago, and I like talking about this in all of my courses. But basically, we took an example system like this. It wasn't AMD Barcelona. It was actually Intel's Core 2 Duo, I believe. And we ran one application, MATLAB, in one of the cores, and the other application, GCC, in the other core, and compared the slowdown each application experienced compared to when it's running alone on the system. So you're running two applications together versus running each application alone. MATLAB slowed down by only 7% here. 1 means it's the same performance as it were running alone on the same system. And GCC slowed down by more than 3x. This is odd, right? The applications slow down very differently when they're running together compared to when they're running alone on the same system, when they have on a two-core machine. So we tried to fix this problem somehow. This is on a real system. We made MATLAB low priority. So you can go into Linux and nice the program, right? And we made GCC high priority. Nothing changed. Basically, you got the same result. So we call this the Memory Performance Hog. Anybody can guess why this is happening? I didn't give you enough information to actually pinpoint the problem, but why could this be happening? Yes? Yeah, that's right. It's some sort of bottleneck or unfairness in the memory subsystem, yes.
Well, maybe that one's triggering more cache misses than GCC, so it has to wait for it to actually go into memory.
That's why it's not slowing down as much?
Yeah, and also preventing the other one from running as fast as it can.
That's right, yes. That's right. That's actually, both of them are true at some level. Okay, I'll keep going, but that's the reason. The reason could be at many places, actually, in the memory hierarchy. It could be in the shared caches, for example. It could be that MATLAB is trashing the cache that GCC is using nicely, but it's not the problem in this case. I'll give you the problem. We'll talk about different problems. But the key question is, can you figure out why there's a disparity in the slowdowns if you do not know how the processor executes the programs? Expecting a no. Who says yes? It's okay to contradict. That's fine. But the answer is no. It's very difficult to do this. And it's even harder to fix the problem without knowing what's happening underneath. I'll give you what's happening underneath because I think this is a very interesting phenomenon going forward. Why do you have disparity in slowdowns? This was the system that we ran MATLAB and GCC on, actually. You had cores, you had private caches, you had some interconnect, you had the DRAM memory controller and DRAM banks. And this is a shared DRAM memory system. This part was shared. And when we ran MATLAB and GCC, this is what happened. MATLAB was very intensive, as you suggested. It generated many, many memory requests that missed in the cache. GCC generated few memory requests that missed in the cache. And memory controller treated these two applications like this. Basically, it kept servicing MATLAB's requests over and over for a long time. And this happened because memory controller was not designed to be fair to applications. It wasn't really aware of the requests coming from different cores. It was just taking in requests, and it didn't know which core was generating the requests. So it was treating them equally. And this is actually the design of many memory controllers today, unfortunately. They're getting better over the research we've done over years, but they're not perfect yet. Okay, so why does this happen? Why does the memory controller do that? You could say, how stupid, right? Why would you ever do that if you're running two applications and not distinguishing between them? Because GCC may be the important application, right? Actually, you may be interacting with your phone. Your email might be the important application, whereas your virus checker is destroying all of the performance of what you're interacting, right? What you're doing, really. So you really don't want this. But this is not a stupid design choice people have made. Well, there are historical reasons for this. And I'll give you, if you know what's going on underneath in the DRAM banks, you would understand those design decisions. So if you look at one of these DRAM banks, this is how it operates. It's basically a two-dimensional array of cells. It consists of rows of cells and columns of cells, and it's much bigger than this, actually. And if you want to access some data, you need to access the row that contains the data first, and that row needs to be first buffered in this hardware structure called row buffer in the DRAM bank. Have you guys seen this before? Which course? 240. How many of you have seen it? Okay, good. So you know about the row buffer. It doesn't exist in everything, but okay. So you need to be able to, you can access a row only from the row buffer. Initially, that row buffer is empty. Let's say the processor, the memory controller, wants to access an address at row 0, column 0. What does it need to do? It first needs to tell DRAM, activate row address 0. Get me this row and place it into the row buffer. That takes a while, actually about 12.5 nanoseconds in modern DRAM. And then it tells the DRAM, get me column 0 from that row buffer. And it takes a while to do that because the data needs to be muxed out. Column needs to be muxed out from that row because the row is long and contains multiple columns, as you can see over here. Okay? So that's now row 0 is in the row buffer. If the processor accesses row 0 again, but a different column, this is called a row buffer hit. Now the memory controller doesn't need to activate the row again because the data is already in the row buffer. You could think of this as a small cache over here. In DRAM, you have to have this cache. It doesn't operate otherwise. And that requires a knowledge a little bit below this one, but I'm not going to go over that right now. When we talk about the DRAM, when we get into the DRAM lectures, you will see why this row buffer has to be there in DRAM. Okay, this is called a row buffer hit, and the memory controller just needs to supply the column address. It's much faster, right, in this case. It doesn't need to activate the row. And the DRAM bank responds with the data. If the processor accesses the same row but another column, again, this is a row buffer hit, and the memory controller needs to only send the column address, and the DRAM supplies a column. Let's take a look at what happens if the memory controller actually needs row 1 when row 0 is open in the row buffer. In this case, the memory controller, what the memory controller needs to do is 3 actions. First, well, this is called a row buffer conflict. You're trying to access row 1, whereas row buffer contains row 0. First, the memory controller needs to write back, if you will. That's an abstraction also. The row 0 into its location in the memory array. And we'll see that abstraction actually operates differently in the circuit level. But that takes some time. It's called a pre-charge. Then the memory controller needs to supply row address 1, and DRAM activates the row, placed into the row buffer. That takes some time. And then the memory controller needs to supply the column 0, which DRAM responds with muxing out. There are 3 steps now. It's taken much longer to service this row conflict compared to the row hit we've seen. Just a second. Yes? Oh, okay. I'll sign it. Thanks. It's like I need to sign some stuff. All right. So we've seen that a row conflict access takes significantly longer than a row hit access. It's about 3 times the row hit access latency. And current controllers, memory controllers, actually take advantage of this. So they make a reasonable design choice. What they do is they prioritize row hit accesses over row conflict accesses, such that they can minimize the latency. They can maximize the use of this row buffer, right? So a commonly used scheduling policy is row hit first, service row hit memory access first, and everything else being equal, prioritize older access over others. And it's a very simple policy too, by the way. So this scheduling policy aims to minimize the latency, maximize the use of row buffer hits, if you will, and maximize DRAM throughput in the end. But there's a downside to it, and this was designed when processors were single core, when you had only 1 core accessing DRAM. It's a great policy, right, if you had 1 core. It turns out it's still not the optimal policy if you have 1 core. You can do much better than this, and we'll see that. Although it's a pretty reasonable policy for 1 core. So in today's systems, multiple threads actually share the DRAM controller. But DRAM controllers are designed to maximize DRAM throughput. They're not designed to actually take into account what's coming from different cores, different threads. As a result, these DRAM scheduling policies are thread unfair. Let's take a look at these 2 principles. Remember, the policy was prioritize row hit requests over other requests. This is bad if you have multiple threads because now you can unfairly prioritize threads that keep hitting in the row buffer, right? Whereas threads that keep missing in the row buffer are deprioritized for a long time. The oldest first, let's assume that the row buffer didn't exist. And you did oldest first scheduling. Oldest first means service the requests that have arrived earlier first. Right? Even this is unfair. This is first come, first serve. Because what happens if you have a very memory-intensive thread that generates lots of requests, the thread that doesn't generate many requests, its requests will be queued behind the other threads that have generated many requests, right? Because you're doing all this first scheduling. Whereas if that thread that doesn't generate many requests were running alone, its request would have been serviced quickly, right away. That's why that thread can see significant slowdown. So these two policies are actually, prioritization policies are actually very unfair. And that's why we see those results. And in fact, it's much worse than that. The memory controller is vulnerable to denial of service attacks. And we've shown that in a paper earlier. And maybe, well, I don't want to add any more labs, but you could probably demonstrate this in real systems today also. It's a little bit harder because people have designed the memory controllers to be better today. But you can actually write programs to exploit unfairness. Let's take a look at one example. And this shows you the importance of understanding all of these different layers, right? Let's take a look at this program. This is a streaming program, if you will. Basically, it does sequential memory access. It keeps accessing memory locations one by one that are sequentially. And it's a very simple program. You have two large arrays, and you somehow initialize them. And then you copy array B into array A, and you do it in a streaming manner, going through both arrays, first locations, copy the first location to the first location in the other next array. And we ensure that each memory access is a cache miss. If you do this, you don't get cache hits, but you get cache misses. Anyway, if you don't understand this yet, think about it later. But basically, it has sequential memory access. And because it has sequential memory access, it keeps accessing the row buffer sequentially. Remember, we had this bank over here and row buffer. Cache line 0 is here, cache line 1 is here, cache line 2 is here, cache line 3 is here, ... Or address 0, 1, 2, 3 is here. And if the thread is accessing this way, which this thread does, it has very high row buffer locality. On a real system, it has 96% hit rate in the row buffer. 96% of the memory requests come from row hits, not row conflicts. And it's very memory intensive because every access is a cache miss. Now we wrote this program, and we call this a memory performance hog, if you will. And we also do a control experiment. You can have the same program, exactly the same program, but make it random memory access. Right? And how do you do that? Basically, instead of copying array B into array A sequentially, you basically copy random elements at random locations. You copy the element at index 1 first, element at index 25 next, element at index 1,000,000 next, and so on. Now you don't have sequential access in the row buffer, right? You have very random access. So this is a thread that has very random memory access because the index is generated randomly. As a result, it has very low row buffer locality, but it's similarly memory intensive. So it has almost the same memory intensity because all of these accesses are actually cache misses, assuming large arrays. Okay, so what happens when you run these two programs together? You have stream and random. What does the memory hog do? Memory hog is a stream. Assume that initially this row buffer has row 0 in it, and stream is generating the blue requests, thread 0 is stream. The first request hits in the row buffer, and then you get requests from random. But stream keeps hitting in the row buffer because it's generating requests that go to row 0. And the memory controller is prioritizing those requests, those blue requests, right? As a result, the random access thread is starving, at least for a long time, at least until stream stops generating requests. Or some memory controllers today have thresholds saying that if a request has not been serviced for n cycles, where n is a large number, force the servicing of that request. Or that may happen, right? But assuming that doesn't happen, with a row size of this and a cache block size of this, a large number of requests of thread 0, stream, can be serviced before a single request of thread 1. And that's exactly, at least that's one of the reasons why MATLAB denies service to GCC. Because MATLAB is sequential access, GCC is more random access. The other reason is GCC is not very intensive, as I showed you earlier. Okay, so now you know at least some problem. Right? If you didn't know how the DRAM architecture, if you didn't know how the memory controller works, then you wouldn't have known how to solve the problem, perhaps. And if you didn't know how the DRAM microarchitecture works, you wouldn't have known why People made the design choice of designing the memory controllers they designed, right? And if you don't know the DRAM architecture, maybe you cannot design a better DRAM controller. Right? So how do you solve the problem? Now that I've given you the problem, I'm not going to give you the solutions. I'll assign you a paper to read by Wednesday. But there are many potential solutions. What is the right place to solve the problem is the first thing, right? Well, the problem is happening somewhere here, but it has implications towards system software, right? Can the programmer solve this problem? I don't know. The programmer has no control over what other program is running on another core, right? So it's very difficult to solve that problem. Although, if the programmer knows that they've designed a multi-threaded program, and they know that it's only their program is executing on the system, they can potentially solve this problem, right? They can construct a thread such that they have good access patterns that do not interfere with each other. So always think about solutions can be specific to the application. If the conditions are satisfied such that the programmer has control over the entire system, this problem can be potentially solvable by the programmer. But in general purpose systems, that's usually not the case. Can the system software solve the problem? Well, that could potentially, right? If it somehow figures out that this application is denying service to the other application, it can take GCC and move it to somewhere else, right? If it has that flexibility, right? And we'll cover some solutions. Or if it has the flexibility to map GCC's data to some other memory controller, it could do that, right? It could keep GCC on that core, but map the data of GCC to some other memory controller. If I'm going too fast, if this is not clear, either let me know, but this could be okay also, because we haven't covered all of these concepts. I'm just giving examples of what you will learn toward this course, toward the end of this course. Can the compiler solve this problem? Maybe tough, right? Because the compiler has no idea what other application is running on some other core. The compiler can optimize this particular program, but cannot optimize somebody else's program, right? You cannot compile Windows, for example. Can you? Somebody else compiles Windows and you execute it. But you cannot compile it, unless you have the source code. Although, again, if you constrain the problem, perhaps the compiler can solve it, right? Again, if only one application is running on the system and you know that, you ensure that, the compiler can potentially orchestrate the threads, scheduling, and the data access patterns. Anyway, I won't go into that right now. Can the hardware solve the problem? Can you fix the memory controller? I assume yes, right? Because the problem is happening at the memory controller. And you'll read one paper that talks about how to fix it. Can the DRAM solve the problem? That's an interesting one, perhaps. You don't fix the memory controller. Memory controller still remains the same. But can you change the DRAM chips? No? Maybe? Any ideas? Yes?
Well, isn't the DRAM controlled by the memory controller?
That's right.
So how would it know, what it can change? Really, the one that's running the show is the memory controller.
That's right. It's difficult to solve the entire problem just purely in DRAM, right? Without changing the memory controller also. But maybe DRAM, you get rid of this row buffer, right? If you could, potentially. At least you eliminate that part of the effect. The sequential versus random access part of the effect. The oldest first, it's very difficult to eliminate at the DRAM level. But you could randomize all the memory accesses such that you get rid of locality. But that's not necessarily solving the problem, because now you have a much worse system. Perhaps because you're not exploiting locality, right? Yeah, well, maybe not equally slow, but much worse than before, right? That's right. Because the intensity also determines how slow something is. You're right. Equally random access. Yeah, it may not be a good solution. Potentially you could solve part of the problem, but it may not be a good solution. I guess there's another question here. Is it a good solution? Right? Can the circuit solve the problem? That's a little bit hard to imagine, right? Okay. But basically, the problem can be solved at many different levels, and it's always good to think about these different levels. In this case, actually, if you constrain the problem, you could solve the problem in potentially all of these levels, maybe except for circuits in this case. So there are two other goals of this course. One is to enable you to think critically. So it's important to look at a solution, look at a problem, and think critically. How do I solve this problem? Is there a good solution? What is the cost and complexity of the solution? Right. For example, if you actually want the system software to solve this problem, you need to somehow expose something to the system software such that the system software knows that this is going on, right? And the MATLAB is denying service to GCC. If the system software cannot figure that out, it cannot solve the problem. Then the key question is, how does the system software figure this out? Well, system software doesn't interact with the hardware at very fine granularity, right? Today, when you schedule a job in Linux, it gets scheduled for 10 milliseconds or so. That's a very long time frame, right? And this kind of denial of service is happening at the millisecond level. So you may be actually denying service for a very, very long time. So you need some mechanisms to expose this to the system software. And that adds to the complexity and cost. So it's good to think critically and figure out what is a good solution. And also enable you to think broadly. That's the second goal. You don't want to design, whenever you solve a problem, you want to consider the conditions and also what is a good place to solve the problem. And there is a big trade-off space. If the system software solves this problem, it's very different from the hardware. But then the trade-offs are different also. And as I said, the compiler could solve the problem if your system is very specific, right? Or the programmer can solve the problem. But the implications are very different. So it's good to think about these different solutions. And over the course of this course, we'll cover many solutions that span these different boundaries. So if you're interested on this, there are some further readings. I've already assigned one reading to you, which is the memory performance attacks, which basically showed the attacks. But if you're interested in one solution, we will cover this solution later on, but you can take a peek at it now, and you can probably take a look at the slides. This is one solution that basically tries to balance the requests coming from different applications, such that you're fair to different applications by changing the memory controller. This is another solution that my student Lavanya proposed with others that basically says we're not going to change the memory controller that much, but what we're going to do is try to figure out the interference that's happening between these different applications and try to map them to different memory channels, different memory controls, such that they don't interfere with each other. This is a more system software solution, and this is a more memory controller solution. And these are very hot topics, actually, in computer architecture today. Today, how to design the memory system of a multi-core processor is a very hot topic because it's one of the biggest bottlenecks. When we talk about the memory system, you'll see that. But we'll cover pretty much the entire system, so you don't need to worry about not learning any component of the system in this course. Maybe not disks. Okay. The takeaway is breaking the abstraction layers between the components and transformation hierarchy levels and knowing what is underneath enables you to solve problems and enables you to solve them efficiently. And we're going to do that in this course. Let's see. It's 1:29. I'll give you another example on DRAM refresh, but maybe this is a good point to stop and take a 5-minute break. Is that good? Okay. Let's take a 5-minute break and be back at 1:35. Resume this. Go into the logistics of the course, if we ever get there. And the other example is from DRAM refresh, which is another problem today that we're facing in computer systems. If you look at DRAM, it sits here in the system. It looks small over here, but it does actually occupy a lot of space, right? How many of you have mucked with the DRAM components of your system? Good, a good number. It does affect system performance, right? Yes, good. You want to have more of it. Okay, but it's difficult to have more of it going forward into the future, and we'll talk about that later on when we cover memory in this course. But DRAM, this thing that I showed you over here that had rows and columns, is actually a two-dimensional array of cells. And a cell looks like this, basically. It's really this data is stored in this capacitor. And that's it. You really want that capacitor in there. But in order to be able to access it, you really need this peripheral circuitry with it, which is the access transistor. And you need to enable or disable the access transistor. And once you enable the access transistor, the capacitor charge is sensed through this bit line, right? That's how DRAM operates. And we'll get into this later on again. But basically, this is the DRAM cell. It consists of a capacitor and an access transistor. And it stores data in terms of charge in the capacitor. If the capacitor has charge, it's a 0 or 1. If the capacitor doesn't have charge, it's a 1 or 0, right? It depends on what value you assign to having charge versus not having charge. But you can store 1 bit this way. And a DRAM chip actually consists of tens of thousands of rows of such cells. This is one row, if you will. It could be 1 kilobits. And you have tens of thousands of rows in the DRAM system. Let's say you have an 8 kilobyte row because you aggregate some chips. You'll see how I get that 8 kilobyte number later on. Let's say you have an 8 kilobyte row and you have 8 gigabyte memory. How many rows do you have in your system? It's pretty simple, right? 8 gigabytes is 2 to the 33, right? And 8 kilobytes is 2 to the 13. So you have 2 to the 20 rows. So it's 1 million rows. It's about 1 million rows. But there's a problem with this circuitry that we need to overcome. Even though it's so popular, we use it everywhere pretty much. This capacitor charge leaks over time. Even if you don't enable this access transistor, it keeps leaking slowly because it's not a perfect circuit. Well, that didn't work too well. But to ensure that the data integrity is maintained, the data that you stored over there remains, the memory controller needs to refresh each row periodically to restore the charge. Basically, this means you need to activate each row every n milliseconds. And this is what existing memory controllers do. This is what happens in your cell phone also. And it consumes energy. To keep the data in your memory, the memory controller, every 64 milliseconds, typical n. Actually, in your cell phone, it could be every 32 milliseconds because they have low power DRAMs. Ironic, but it could be every 32 milliseconds. Every row is refreshed every 32 milliseconds. And this consumes a lot of energy and performance overhead. So what are the downsides of this? Well, you need to do this to maintain correctness, right? You don't want to lose your data in memory. But there are downsides of it. One is it consumes energy. Each refresh actually consumes energy. It's basically what we talked about. It's basically an activate. You don't do the read because you don't need the data. You just need to activate it such that it's refreshed. And actually, you need to close the row also. So you do two of the 3 steps that we've discussed. And that consumes energy. And that also degrades performance, right? Because while you're refreshing this bank, nobody can access it, right? Because you're refreshing that bank to maintain data. And this leads to quality of service impact. It could be when you need that data as a user, the bank can be refreshing, right? And it could lead to long pause times. And finally, going forward, this rate at which you refresh the DRAM limits this capacity scaling of DRAM. Because as you increase the size of this bank, as you add more rows, you need to refresh more rows. Right? And as you reduce the size of the cell, it becomes much harder to maintain the charge in a much smaller capacitor and in a much more leaky access transistor. So there's a problem going forward. And I'll show you some example of this problem published last year. But basically, on the x-axis, this shows the capacity of the device, DRAM chip itself, from 2 gigabits to 64 gigabits. These are real today's devices. And these are future projected devices. And this is the percentage of time spent refreshing. The device spends refreshing. Today, it's about 8% with 4 gigabit devices. And it's going to increase into the future. And even 8%, you don't want to lose it. And this number is actually debatable. But the trend is correct in many different systems. So basically, if we want to have a huge memory, which we would like to, especially with the trends that we're seeing, we're having increasingly intensive, data-intensive applications. We want to have more data stored, right? You guys are living in a time where data is going to overwhelm everyone. And we want to store it in memory, and we want to access it quickly. We want to analyze it quickly. We want to make inferences from it, right? Many, many things are like this in today's application space. So we want to keep memory large. But if we keep memory large, DRAM large, basically 46% of its time will be spent refreshing. Half of the time it will be unavailable. It sounds pretty bad, right? If we keep the current way of doing refresh it every 64 milliseconds, or every n milliseconds. And this is the overhead in terms of energy. Again, this is device capacity on the x-axis and percentage of DRAM energy spent refreshing. Today we spent 15% of the memory energy, memory system energy, which could be significant. Memory system energy can consume about half of the entire system energy. In fact, IBM had done studies on this. There are many other studies also from Google too. But studies show that big data center servers, they spend approximately 40 to 50% of their entire system energy on the memory system. and the rest on the processors and the interconnect and the caches. And 15% of that 50% is spent on refresh for this DRAM, at least. And well, it may not be 15% of that exact 50%, but 15% of the DRAM energy. And going forward, this will increase also, right? 50% of the energy, DRAM energy, will be spent on refresh. So obviously, this is a problem. And as an architect, when you're architecting systems, you would like to figure out these problems and solve these problems. So how do you solve this problem? I'll give you one potential solution. And it requires knowing what's going on underneath, what happens in the system. We may ask the question, do we need to refresh all rows every 64 milliseconds, right? What if you knew what happened underneath and exposed that information to upper layers? What is that underneath? If you look at DRAM, today, what the memory controller is doing is treating the entire DRAM uniformly, thinking that it needs to refresh every row every 64 milliseconds, right? But if you knew how DRAM was composed underneath, you would know that it looks like this. Basically, there are very few memory rows that need to be refreshed every 64 milliseconds because they can retain data for a time period between 64 to 128 milliseconds. There are some other memory rows that need to be refreshed every 128 milliseconds, 2x, or half the period, or twice the period, half the frequency, because they can retain data between 128 to 256 milliseconds. And most, actually overwhelmingly most, memory rows can be refreshed at every 256 milliseconds because they can retain data for much longer. And if you knew this, you could say, why are we refreshing everything every 64 milliseconds, right? It makes no sense. Because perhaps you could do something about these things, and perhaps you could refresh only these rows, if you knew them, every 64 milliseconds, and everything else every 256 milliseconds. Right? And since most of your rows in the entire DRAM system falls into this huge bin, now you can get rid of almost 75% of your refreshes, right? Because 64, instead of refreshing most of your rows at every 64 milliseconds, you're refreshing them at every 256 milliseconds, 4x the period. Does that make sense? So that's the idea. If you knew what's going on underneath, if you didn't know this information, then you keep doing business as usual, right? What is business as usual? Refresh everything uniformly. But the structure of retention time, how long a row can retain data, is actually non-uniform in DRAM. And the curve actually looks like, kind of like this. This is retention time. And this is, I guess, number of rows. It kind of looks like this. And 64 milliseconds is right here. And most DRAM rows, actually, the mean is about maybe 10 to 100 seconds over here. So DRAM is not that bad. And you could take advantage of this. Right? So why does this happen, actually, just as an aside? Why do you think cells are different in terms of how long, capacitors are different in terms of how long they can retain data? Yes?
Manufacturing isn't perfect.
That's right, exactly. You have significant variability in the manufacturing. Not all of the cells are exactly the same. Some capacitors are a little bit larger. Some access transistors are a little bit larger or smaller or defective. As a result, you get very different retention times across different cells. And this could be due to systematic errors or non-systematic errors in the manufacturing. And in fact, this retention profile is after manufacturers test for many defective cells. So what DRAM manufacturers today do is they test every single row, and they try to get rid of those rows that do not retain data for even 64 milliseconds. Today, presumably, all of the DRAM chips that you use should retain data for at least 64 milliseconds without being refreshed. But that may not be true going into the future either. Okay? So we have this profile because manufacturing is not perfect. So how do you take advantage of this profile? So we've gone into the manufacturing level, right? The process level. If you could expose this retention time profile information, who would you expose it to? Do you expose it to the memory controller? Do you expose it to the operating system, the programmer, the compiler? All of these are actually could be valuable. So you could expose to the memory controller, right? If the memory controller knew which rows needed to be refreshed every 64 milliseconds versus every 128 milliseconds versus every 256 milliseconds, it could refresh each row according to how often it needs to be refreshed. That way you could reduce the number of refreshes significantly. And that's one idea, actually. I'll give you some results very briefly based on that. But there are other options, and this could be reasonably simple, although there are a lot of complexities related to this. We'll get to this. The second, you could expose to the operating system, right? If it looks really like this, you can tell the operating system, oh, these rows in DRAM, if you have that interface, actually do not retain data as long as 256 milliseconds. So don't allocate them to anyone. Right? If the operating system knew that, it could do it. And that could be a nicer solution, right? You lose some DRAM capacity, sure, but maybe it's tolerable, right? If it really looks like this. And I'll give you some data on actually how many of these rows exist. Programmer? Now you're becoming perhaps more specific to the application, right? If the programmer actually has control over allocating their data to rows, which most general purpose systems don't, because you don't know where your data goes in DRAM, right, when you write a program. But if you do, if the programmer has that control, then maybe it's not a bad idea. If the programmer knows how long their data is needed. For example, if the variable is really temporary, you could construct a row of variables that are really temporary and never refresh that row, because the variables really are not going to be used beyond 64 milliseconds anyway. Right? So you could come up with creative solutions like that if you have a lot of control on your system. It's not very general purpose. You don't want average programmer at Microsoft trying to do this, right? Not good, because they cannot even write real programs today. This is not to mention anything bad about Microsoft, but that's true for average programmer anywhere, right? If you like to write programs quickly and correctly, if you really need to worry about refresh, well, good luck writing programs quickly and correctly, because it's already difficult to write big pieces of software that works correctly today, right? Because the software is very, very complex. If hardware is complex, software is much, much more complex to design. I'm not saying hardware is simple. It's complex, but software is much more difficult to verify. At least we have a shot at verifying some of the hardware that we have today. The compiler could actually make use of this information also, again, on a specific system, right? If the compiler has a way of allocating data to a particular memory row, it can say, oh, this data doesn't need to be accessed beyond this time, so maybe I'll allocate it to a row that will retain the data without being refreshed. And people have proposed similar solutions. So this is an interesting thing to explore if you have this problem. But you need to know what's going on underneath. How much information to expose? That's another question, right? Do you expose the retention time of every single row? We discussed that there are at least 1 million rows, right, in an 8 gigabyte memory. What if you have the terabyte memory? Going into the future, we want terabyte memories. Many servers actually have terabyte memories. What is a terabyte? To the what? Is it to the 40? It's to the 40, right? Yes. What is a petabyte? Is it to the 50? And the exabyte is to the 60? Well, what if you had an exabyte memory? Good luck, right? Then you don't want to expose every single row's retention time to some upper layer, because that's a lot of information in and of itself, right? You'd really like to bin these, as we did over here. This is a binning, right? You have 3 bins. But it could be much finer granularity than this. So this affects hardware and software overhead, power consumption, complexity, cost, and a lot of things. And perhaps an even more difficult question is, how do you determine this profile information? How do you figure out which cells have what kind of retention time? Which rows have what retention time? And who figures this out? I'm not going to give you the answer, but it actually turns out to be tough to do this. I'll give you a hint, but it turns out some of the rows, some of the cells, move between different retention time states. Sometimes they retain data for 64 milliseconds, sometimes they retain data for 1 second. And again, this is a circuit level effect. What happens is, in the access transistor, sometimes randomly charge gets trapped. And once the charge gets trapped in the access transistor, the capacitor leaks much more quickly. And this, it turns out that this is a random process. It happens just randomly over execution time. It's very hard to control. Actually, it's impossible to control from what we know. So you really want to know the minimum retention time of a given cell to be able to figure out this information. So this gives you an understanding of what you need to do to solve an important problem, right? You really want to go underneath. That's why we would like to break the abstraction layers here. So I'm not going to go over this, but I'll give you some data. But this is a retention-aware intelligent DRAM refresh, which solves the problem by exposing the information to the memory controller, exposes little information by binning the rows, and assumes that this profile information is accurately obtainable. It doesn't solve this problem. So if you look at this, is actually data from Samsung, Samsung's DRAM chips from a paper they published in Electron Device Letters in 2009. But if you do the math, in a 32 gigabyte DRAM system, only 1,000 rows, 1,000 cells, 1,000 rows need to be refreshed every 256, more frequently than every 256 milliseconds. That's very small, right? So that kind of shows that this curve over here. So the key idea is to refresh rows containing weak cells more frequently, other rows less frequently. To be able to do that, you need to profile the retention time of all rows. You need to store the rows into bins by retention time in the memory controller somehow. And you can do efficient storage with Bloom filters. How many of you know Bloom filters? A few of you, a little bit. How many of you do not know Bloom filters? Okay, so we're going to cover that. I'm not going to cover that right now because I want to go into some logistics. But remind me to cover it if I don't cover it. We're definitely going to cover it toward the end of the lecture. But this is something that you really should know. It's a compact well, maybe I'll cover it now. What do you guys think? It's a compact representation of a set, basically. It's an approximate representation of a set. Basically, let's say, I'll do it specifically with this example over here. Let's say you want to store information about set membership. You want to know whether some elements are in a set or not. Bloom filter is a very good structure, approximate structure, to tell you whether an element is in the set or not. So let's say we have all these rows in memory. Let's say we have how many rows? 0 through 1 million minus 1, right? If you want to know whether a row needs to be refreshed every 256 milliseconds or every 64 milliseconds, you can keep a bit for each row saying it needs to be refreshed every 64 milliseconds, right? If it's not in this, if the bit is not set, then you're going to refresh it every 256 milliseconds. That's the idea. And there are very few rows, right? There are only 1,000 rows over here that need to be refreshed every 64 milliseconds. Otherwise, you refresh it every 256 milliseconds. So about 1,000 rows, bits are set. But the problem, well, I guess I shouldn't add more. If the bit is set to 0, then the memory controller checks the bit and says, oh, the row doesn't need to be refreshed every 64 milliseconds. It can be refreshed every 256 milliseconds. So this is one way of representing the membership of each row in the bin that says refresh every 64 milliseconds. That's the bin. If the bit is set, yes. If the bit is not set, no. But this is not approximate, right? This is exact. You have 1 bit per every row in the system. And it has a problem, right? The problem is you have 1,000,000 bits. Well, what if you had an exabyte memory system? Then this structure needs to grow significantly, right? It needs to be huge. 1 bit per row. The realization is that you don't need to keep this data structure exact. You can reduce it to a much smaller bit vector and allow some collisions. Maybe instead of having 1 million, you have 1,000 bits. Right? And now if you want to, you know that some rows need to be refreshed every 64 milliseconds. And you know those addresses. Now you need to insert them into this bit vector. This is called a version of a Bloom filter, a poor man's version. It's a very simple one. Let's say row address 56 need to be refreshed every 64 milliseconds. You indicate this by hashing the address through a hash function and setting a bit that's determined by this hash function. If this bit is set, any element, any row address that maps to that bit through that hash function needs to be refreshed every 64 milliseconds. So you have now a much smaller bit vector. And you insert those rows that need to be refreshed every 64 milliseconds going through this hash function. You can have multiple hash functions also, right? Eventually, you have a bunch of bits that are set to 1, right? Does that make sense? And the bits that are set to 0 mean that elements that map to those zeros should not be refreshed every 64 milliseconds. But now you have a much smaller structure, but it's approximate. Because some rows that actually do not need to be refreshed every 64 milliseconds may go through the hash function. This address may be hashed, and that address may happen to map to a location whose bit is set by some other address because you have a collision between different addresses because you do not have enough bits, right? You don't store 1 bit per row. You basically store 1,000 bits for 1,000,000 rows and indicate the membership of an address going through a hash function, right? And setting a bit that corresponds to that hash function and the address. So that's the idea of a Bloom filter. You can represent set membership with a much more compact data structure. It could be software, it could be hardware, right? This is much more implementable in hardware, right? The upside, it's simple, right? And it's less, it's less hardware cost if you implement in hardware. And less storage cost in general if you implement in software. The downside, well, I've already told you the downside, right? You have what's called false positives, right? Meaning you're trying to test the membership of a row in this bin. And even though the row may not need to be refreshed every 64 milliseconds, this structure tells you, yes, you should refresh it every 64 milliseconds, right? That's called a false positive. You really shouldn't refresh it, but you're refreshing it. Well, in this case, it's OK, right? If you refresh a row more frequently than it's needed, it's OK. You just waste some energy, but you're still correct. So Bloom filters are useful in cases when false positives are tolerable. Basically, whether you're checking if the membership check gives you a true, that's harmless in terms of correctness, right? Okay, so that's the idea of a Bloom filter. You could use this for many, many purposes, and we'll actually talk about other purposes later on. But the key takeaway is it's a compact, approximate data structure to represent set membership. And represent and quickly check. I'll add that. Set membership. It could be used in hardware, software. You could have multiple bit vectors. You could have multiple hash functions to reduce the probability of collisions. And if you want to learn more about it, you can read Bloom's paper in Communications of ACM in 1970. I should have a reference somewhere later on. It's an old data structure, but it's very powerful. Anyway, OK, in this case, Radar, this mechanism uses these Bloom filters to store information about which rows need to be refreshed at what frequency. And that's why the hardware cost is really low. If you actually needed to do this, the hardware cost would be much higher. OK, and once you have this information, the memory controller refreshes rows in different bins at different rates. Now you can do that refreshing. So I'll give you some results. In computer architecture, actually later on, we'll see a lot of results. One question that you should be asking perhaps right now is, actually, how do you evaluate something like this? Do you manufacture DRAM and test it? Well, that's a lot of money Yes.
You simulate it?
Exactly, you simulate it, right? In this case, we simulated it. And core system. Actually, you will write a simulator through the course of this course, again, where you would simulate the memory system of a processor. The last lab will be a simulator that you write where you would simulate the operation of cache coherence in a multi-core processor. That'll be the easiest lab, hopefully. But it should be fun. But here, again, we simulated these mechanisms with an 8-core system, 32 gigabyte memory, with different kind of workloads. SPEC is Standard Performance Evaluation Corporation, and some database workloads. We measured about 74.6% refresh reduction at this storage. So this is what you would expect, right? Because most of the rows don't need to be refreshed. Most of the rows can be refreshed every 256 milliseconds. And this leads to, in these workloads, 16% dynamic power reduction in DRAM and 9% performance improvement. And you could actually simulate different DRAM capacities also. And we saw that the benefits increase with DRAM capacity. Anyway, you'll probably take a look at this paper later on in this course. But it's good to, then we won't cover it as long. But this is a good example of exposing information to the upper layers by understanding what's going on underneath at the circuit level and taking advantage of what's going on at the manufacturing process level. Right? And if you want to learn about this, this is the paper that talks about this. And this is a more general paper that I wrote on memory scaling that talks about general issues in memory. OK, what is the takeaway? Again, breaking the abstraction layers between components and the transformation hierarchy levels and knowing what's underneath and exposing it enables you to solve problems and design better future systems. In this case, this is hopefully a better future system. It doesn't exist today. Maybe it will never exist. But maybe some of the ideas that are generated over here can enable the design of future systems. Right? And the second takeaway, I think, is if you have cooperation between multiple components and layers, you can enable much more effective solutions and systems. Again, in this case, you can cooperate between the DRAM and the memory controller, or you can cooperate between the DRAM and the operating system, right? Even though in this case we evaluated the memory controller, you could say those rows are exposed to the memory operating system, and operating system doesn't allocate any rows that cannot retain data for at least 256 milliseconds. OK, let's see if we have time to finish. Oh, we do have time. That's good. I'll keep you for 15 more minutes. Sorry. So what are the goals? This is actually the real thing that I would like to cover. But I think the real thing is what I really covered before. You're here for the technical thing, right? Technical material. So but let me go over some of the course logistics very, very quickly. Basically, we would like to teach, enable, and empower you, I guess you, to understand how a processor works. The first step is really understanding. If you would like to do what I've discussed, you really need to understand what's going on. Right? Second, well, you need to also implement. You need to know how, you need to put your understanding to test, right? And you will implement a simple processor with not so simple parts. You need to understand how decisions made in hardware affect the software and the programmer, as well as the hardware designer. And I'll keep harping on this, because you will make a lot of decisions, and we'll consider a lot of decisions that have implications across the stack. Well, another goal is to think critically, of course, in solving problems. And I'll assign you many readings, as well as in lectures. We'll talk about a lot of different options. Thinking broadly across the levels of transformation. Because solutions that are confined to one level are increasingly less effective as we design much more complex systems. So you'd like to find the solutions that are best across the levels of transformation. And also understand how to analyze and make trade-offs in design. And you will do that some in your labs, especially in the extra credit portions. We'll ask you to design different things. And that you can exercise your creativity that way. So agenda, well, we're just starting the lecture, right? So this is the agenda of this lecture. We'll talk about course logistics, what Forward 7 is about, lab assignments, homeworks, readings, etc. But I guess this is one of the important takeaways. We have a bunch of assignments due in the next 2 weeks. Homework 0 is due January 22nd, and I'll talk about that. Homework 1, this is basically a very simple thing. Homework 1 is due January 29th, and the lab 1 is due January 24th, which is next Friday, basically. So you better get on it today. Well, I guess you cannot get on it today because the lab handout is not up yet, but it'll be up Wednesday. Well, we're not going to get into basic concepts in computer architecture because we've already talked about a lot of it right now. but in the next lecture. So there are handouts for today. They're online, homework 0 and syllabus. Let's see if I go into, if I can, I'll show you, go over briefly parts of it. So how do I find, this is usually how I find things. There you go. So if you go into the website, a lot of things, well, pretty much everything will be online in this course. You can find the syllabus. And we didn't want to kill trees, so you'll have to look at it online. You can feel free to print it. But basically, take a look at the syllabus. I'll cover part of it today. And the second handout, let me go over that too. Actually, let me do this. Open link in new tab. And I'll go into homeworks. Second thing is the homework 0 handout, which basically asks you to answer a bunch of questions about yourself so that we get to know you. Although it's not updated yet. And you should definitely attach a photo so that at least I can get to know your name. Or at least associate a name with the picture, right? Okay, you'll submit this electronically. Okay, I'll cover that briefly later on, but let me introduce the course staff as much as they're here. This is me. You've probably seen me or known about me. But basically, my office is at CIC, Collaborative Innovation Center. How many of you know where it is? How many of you don't know where it is? Oh, okay. So you'll need to know. You'll need to learn. If you basically, well, you don't have to, I guess, if you don't come to office hours. That's okay. It's the Collaborative Innovation Center. It's the white building, 4720 Forbes Avenue. It's the first building right after the bridge, the bridge on top of Neville Street. My office hours are this, for now at least, or by appointment. You can figure out my webpage. I've been here for 5 years now, and I got my PhD from UT Austin, worked at Microsoft, Intel, and AMD, and consulted for other companies too. But I like looking into computer architecture and computer systems in general. My group does research in many different areas. I'm happy to talk about that, and you'll see some of that research. Actually, what we've talked about today was research that was done by me and my group over the years. The memory performance attacks that we described, we did that while I was at Microsoft Research, for example. And the radar work was done by my students last year. Okay, so there's a lot of interesting things in architecture, actually. It's good to take a look at different things. And we have a bunch of bright TAs also that will help you survive the course, hopefully. Rachada is my PhD student, who's sitting over here. He's set up that recording equipment, so you know him by now. Varun, I don't know if he's here. He has a class at this time, but Varun took this course, I guess, in spring 2013. Actually, all of my TAs took this course. Other TAs took this course in spring 2013. Xiao, he's not here? Oh, I thought he was coming in. Okay, he also took this course at that time. And Parash, I guess he's not here either. Oh, he was at the door. Oh, he's still over there. He's shy, I guess. You can come in. I was introducing you. Okay, this is Parash. He also took the course in spring. Well, you can sit over here if you want. Unless you don't want to be here. Oh, okay, Xiao is also coming. Hurry up. You came at the right time, but you missed it a little bit. Yeah. This is Xiao, and he took the course in spring 2013 too. So they'll help you a lot. And we have 4 TAs. And your turn will be in homework 0. That's why we have homework 0. It's absolutely required. You cannot get a grade in this course if you do not turn this in with a picture. And while answering all of the questions over there, I read these. And I might send you an email about those. This is your opportunity to tell us about yourself. It's due January 22nd, midnight. Yes, that's absolutely required. And you'll submit via AFS. I think that's what we've decided, right? Every assignment will be submitted through AFS. And all grading is predicated on receipt of homework 0. Your grade will be 0 if this homework 0 is not completely turned in. On time. by midnight, January 22nd. It's not that hard. Okay, where do you get up-to-date course information? Well, website is really your place, because the website actually contains pretty much everything. And I'll show you the website from last semester, not last semester, last time I taught the course. And we're going to cover a similar structure. So this is a website from spring 2013. We're in 2014 now, for those of you who have not made the adjustment to the year yet. But basically, you can look at this website to see kind of what's coming. We actually have I don't know what's happened here. We actually have the entire material that we covered in spring 2013 up, and we're not going to take it down. You can look at the lectures, you can look at the buzzwords, you can look at the videos, you can watch the videos. You can look at the exams. We're not going to take that down either. If you click on the exams, you can see what's coming, potentially, this semester. You can look at the solutions. I would suggest doing the exams before you do the solutions. But all of them are up. So you have a wealth of material from spring 2013, as well as spring 2012, that you can look at. But this will be our website, spring 2014. OK, well, let me go back to this. Blackboard, well, I'm not sure if this is true anymore, right? We're not going to have any homeworks uploaded to Blackboard. OK, so we're going to minimize the use of Blackboard. Let's do this. Let's not be like that computer that gave me an iced tea. OK, your email me and the TAs, and also Piazza, right? We have a Piazza set up for your questions. If you go to the website and click on Piazza, you will find that. Looks like I'm not. If I allow this, nothing happens. OK, and why does it ask me to allow it, right? OK. OK. Let me talk a little bit about the lectures and recitations. Lectures are here, and attendance is for your benefit and is therefore important. Participation will be important. And some days we may have recitation sessions. We have recitations. We have 3 recitations. Differently from last semester, these are not only lab sessions. These are real recitations where the TAs can help you with pretty much everything in the course. You can attend any session. You don't have to attend the session that you're registered for. And the goal of the recitation is to enhance your understanding of the lecture material, help you with homework assignments, exams, and labs, and get a one-on-one help from the TAs on the labs. The Friday recitation will be also a check-off session for the labs when a lab is due. But recitations are actually places where you should go to enhance your understanding. And I'd recommend that everyone go to one recitation, or more recitations. You can actually go to any and all if you wish, if you have the time, yes.
So you said Friday was a checkoff?
No, Friday is a recitation, but when there's a lab due, you can check off your lab on Friday also.
On Tuesday, Thursday?
Absolutely, yeah. You can get checked off anytime, actually. You can get checked off with an appointment. Friday is usually the deadline of the labs, and you should get checked off. For example, for the January 24th lab, the first lab, you should get checked off by the end of the recitation session on Friday. But recitations are much more broader than labs. So definitely attend recitations in addition to lectures. Tentative schedule, actually, I just showed you the schedule from spring 2013. The schedule is in syllabus, but you should really look at spring 2013 website to see what kind of topics we're going to cover. Again, don't believe that schedule. We may change it dynamically. Well, I guess I'll not talk about this. I will not go through this digression now. But systems in general that perform best are dynamically scheduled, right? I cannot tell you that we're going to execute this instruction on January 22nd, right? That's not going to happen because we may not be able to cover. Maybe there's something important that's going on January 22nd that makes me want to talk about that, right? Because it's important to give the context of current events. And well, we'll talk about compile time, runtime later on. OK, what you will learn, you'll definitely learn computer architecture. This is the science and art of designing, selecting, and interconnecting hardware components and designing this hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. This is the definition I wrote in your syllabus. But there's a traditional definition that we will distinguish from. This covers basically a lot of parts of computer architecture. It's not traditional computer architecture. Traditionally, computer architecture is defined as the ISA, instruction set architecture, the interface between the hardware and the software. And this is Amdahl's, Gene Amdahl's definition. he designed a lot of the computers, including IBM 36091, which we will talk about, which had out-of-order execution in it, out-of-order processing of instructions. But his definition was the term architecture is used here to describe the attributes of a system as seen by the programmer, i.e. the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. So he's actually referring to this difference in the transformation layers, right? As seen by the programmer, that's the ISA. And this is different from the organization of the data flow and controls, microarchitecture, logic, right? And this is Gene Amdahl. I guess he's looking at a circuit board with a 100-gate LSI air-cooled chip, 100 gates. Okay, so this is one of the readings that you should do, which talks about the levels of transformation. It's an old reading that doesn't talk about multi-core as much, but it's still important because it talks about the transformation layers, as well as some of the things that we are going to cover in the next few lectures. So this is your required reading. And we've talked about the user-centric view. It's good to think about user as part of this transformation hierarchy because we're going to design computers for users, right? And the entire stack should be optimized for the user. Actually, let me skip to something because we don't have that much time left, right? Yeah, I don't want to keep you for long. I'll start on I'll start with this later in the next lecture. But basically, this course is classified under computer hardware. But this is not a hardware course per se. You'll learn a lot about hardware, but it's going to be very, very important to master both hardware and software. You'll be much more successful in your life as an engineer, or in general, whatever you choose to do from now on, if you know both of the parts, if you know the entire system rather than a specific component. Because you can develop better software if you understand the underlying hardware, and you can design better hardware if you understand what the upper layers need. And you can design a better computing system if you understand both. Okay, so we'll cover the hardware-software interface and the microarchitecture and focus on trade-offs and how they affect software. So hopefully you have this required background. So I'll start with this later on, but let me say this. How you prepare and manage your time will be very important in this course. And there will be assignments. There will be an assignment to almost every week, 7 labs and 7 homework assignments. And labs will not be easy. It will be a heavy course. Homeworks will not be easy also. We'll have lots of, but homeworks are there to just to make sure that you're actually prepared for the exams. Because the homeworks, actually this should be 7 over here. I think we didn't count the last homework last year. That's why this says 6 over here. But homeworks are only 10% of your grade. 7 lab assignments are 35% of your grade. There are 2 midterms, 1 final, and participation plus our evaluation of your performance is 5%. This is more subjective, but for example, if you tanked midterm 1, and if you were sick on midterm 2, but if you got 100% on the final, that says something, right? So that helps us. This 5% helps us to give you more credit for doing that. Whereas if you tanked all the exams, it's going to be tough to recover that. So we'll take into account your progress over the course. If you're actually improving significantly over the entire course, then that's a good thing. Okay. I think you can take a look at the syllabus for these, but a little bit about the labs. These will take time, and definitely start early and work hard. This time we're going to do the ARM ISA. This is going to be an experiment. We've traditionally been using the MIPS ISA. How many of you know the MIPS ISA? Done anything with the MIPS ISA? Sort of? 1, 2. How many of you know the ARM ISA? Oh, good. A little bit better. How many of you know the x86 ISA? No meaning really have implemented a processor? So next time it'll be x86, so you're lucky this time it's ARM. But this will be an experiment. So we're transitioning the labs to ARM. But this is very important. The red parts are important. And labs will be done individually unless specified otherwise. This is, we've done it last semester, and we received very good feedback on this. And you'll have a total of 5 light lab days per semester. Okay, I'll start with this. This is not the most exciting topic that I'll talk about, but you're all CMU students, so hopefully you'll obey this. I will not tolerate any form of cheating. This is very serious, and this has happened in the past. And we should not be doing any cheating. A lot of the assignments, actually the homework assignments will be similar to past classes. I would suggest that you don't copy the solution. or any solution for the labs even. And you're all adults, and we will treat you to do so. If something is an individual assignment, it's an individual assignment. You don't talk to others about it. You do the assignments, you talk to the TAs, and they will help you. They'll help you a lot. We have 4 of them, and they all are excited about helping you. So please don't make me go through all of these documents. If I have to go through them, I will go through them. But cheating will lead to failing grade and no exceptions, and perhaps more, depending on the policy over here. But basically, make sure that everything is your own work. Homeworks, I'm open to collaboration over here, but all homework write-ups must be your own work, written up individually and independently. However, you can discuss your homeworks with others, but labs, you really need to do them on your own. Okay, so these are the homeworks for next 2 weeks. Homework 0 is due next Wednesday. Homework 1 is due Wednesday, January 29th. And this will have an ARM warm-up, ISA concepts, and basic performance evaluation. And this is the lab assignment 1. And we will talk about this in more detail on Wednesday. I guess I won't keep you much longer, because there might be another class coming here also. And we're already slightly over time. But any burning questions for now? Everybody's excited about the course? Yes?
Is the homework 0 up to date right now? Because I just forgot about it.
Oh, okay. Homework 0. Is the homework 0 up to date?
It says something about submitting a hard copy, so is that currently correct?
Oh, no, AFS is currently correct. That's why it's not up to date. Okay. But we should update the homework 0 such that it's not hard copy anymore, and also the last question that we were going to add. Okay, I'll see you Wednesday.